today's class we will study module 2. So, that is in the module 2 we have now micro network theory and passive devices. It contains two parts, one is the micro network theory and another part is passive devices. Here we will study what are the basic things or the requirements are there in order to understand this micro network. And in the passive devices we are studying the different types of the passive devices which you are using for this microwave network. Now let us see what is meant by this microwave network. Micro network is an interconnection of various microwave components and devices such as attenuators, resonators, amplifiers, phase shifters, etc. And these are connected to a transmission lines, that is either coaxial cables or through a waveguides. Before studying the micro network, I will have a little a glance on low frequency networks, and then we will study the detailed things related to the microwave network. Now let us consider here you have a low frequency 2-port network, and this is our input, okay, and this is our output. Okay. Now at the input we are applying the voltage V1, and at the output we are getting the output voltage V2, and I1 is the current due to the voltage V1, and I2 is the current due to this voltage V2. And in order to analyze this particular low frequency networks, we are using the different methods or the techniques. One is a Z parameters, another one is Y parameters, another one is H parameters, another one is the ABCD parameters. That is Z parameters, Y parameters, H parameters and the ABCD parameters are used to analyze these low frequency 2-port devices. Okay. Now if I look into this Z parameters, the voltage V1 is equal to Z11 into I1 plus Z12 into I2. So this particular voltage, and the voltage output voltage V2. So V2 is equal to Z21 into I1 plus Z2 into I2. Here I1 is the current at the input side and I2 is the current at the output side. And these what are the relations are there, V1 in terms of I1 and I2 and V2 in terms of I1 and I2. So you can write it in this matrix form. So you can write it as V1 and V2, and this Z11, Z12, Z21 and Z22, then I1 and I2. Okay. Now using this particular matrix we are analyzing the 2-port network. Now coming to the Y parameters. Now for the Y parameters is there I1 equal to Y11 into V1 plus Y12 into V2 and I2 equal to Y21 into V2 plus Y22 into V2. Now here if you look into this whatever Y11, Y12, Y21 and Y22 are there, so these are the admittances. Now these equations, okay, I1 and I2 which are represented in terms of voltage and admittance, so you can represent in the matrix form. Okay, when you represent in the matrix form, okay, then I1 and I2, then this Y11 and Y12 I am writing in one matrix form and V1 and V2. Now, this is also we are using to analyze these low frequency 2-port networks. Now coming to the hybrid parameters. In the hybrid parameters, we are having the two values, one is the V1 and the other one is I2. So V1 is given by H11 into I1 plus H12 into I2, and I2 is calculated by H21 into I1 plus H2 into V2. And these two equations, once again if I write it in the matrix form, so I can write it as V1 and I2. So this is equal to Okay. H11 and H12, H21 and H22, then I1 and V2. Okay. So, then if I take the ABCD parameters, so to analyze this low frequency networks, then V1 equal to AV2 minus BI2 and I1 equal to CV2 minus DI2. So, then you can write it in the matrix forms. Okay. Now, so these 4 parameters we are using to analyze this low frequency networks. So, these methods, the 4 methods, we are not using to analyze or study the micro networks. So, because of some issues, so the major issues are 3 issues are there. The first issue is non-availability of terminal voltage and current measuring devices. That is, we do not have any devices to measure the terminal voltage and the current at the high frequencies. And the second one is, at high frequency, open circuit and the short circuit conditions have not been easily achieved. I mean to say that at high frequencies, it is very difficult to achieve open circuit and short circuit conditions. And the third one is, presence of active devices makes the circuit unstable under the short circuit and the open circuit conditions. Means to say that in a micro network, we are using some active components. So, due to the presence of this particular active components, the circuit becomes unstable under short circuit and the open circuit conditions. Okay. Due to this instability, so these particular methods cannot be used to analyze the microwave networks. So, let us consider the reciprocal network. Now, for a reciprocal network, the transmission line characteristics are similar in either directions. So, that means to say that from input to the output or from output to the input, so the characteristics are similar. And now let us consider one multiport network, so consisting of n number of ports. Now, for this particular network, I am representing the incident voltage by Vn plus and a reflected voltage by Vn minus. Vn plus is indicating the incident voltage and Vn minus is indicating the reflected voltage. Okay. Now, the total voltage is equal to 0, that is the total voltage Vn equal to 0 for all the n ports except the ith port where the fields are EI and HI. Okay. Now, once if I consider, so this is one reciprocal network. Okay. Now, here my incident voltage is there, so this is Vn plus and my reflected voltage is there, so this I am taking it as Vn minus. And the total voltage Vn I am representing, so this is equal to 0 for all the n ports except the ith port where the fields are EI and HI. It means to say that except the ith port, okay, from all the ports, so that is Vn equal to 0. But for the ith port, so the Vn is not equal to 0. Similarly, the Vn equal to 0 except the jth port, okay, where the fields are Ej and Hj. Now, for the jth port once again, so the Vn is not equal to 0 where the fields are Ej and Hj. Okay, repeating once again. Now, for this is our network and Vn is the incident voltage and Vn minus what it is represented, it is a reflected voltage, and we are considering the total voltage Vn equal to 0 for all the n ports which are there in this particular network except the ith port where the fields are EI and HI. That is, for the ith port, the fields are EI and HI where the Vn is not equal to 0. Similarly, for the jth path, the fields are Ej and Hj where the Vn is not equal to 0. And now, the meaning of this is that except I and j for all other ports, so this particular Vn is equal to 0. Now from the Norin's reciprocity theorem, you can write it as, see this is a surface integral Ei into Hj minus Ej into Hi, okay, into ds is equal to 0. Okay. And where Ei is the E field and Hj is the, Ei is the electrical field and Hj is the magnetic fields. Where this S is there, okay, it is a closed surface area of conducting walls enclosing the junction N ports in the absence of any source. Okay. Now, closed conducting walls, what the word has been written in this, it is related to the waveguides. Now, for the N ports you consider, now for the what the Norin's reciprocity theorem is saying is that an integral from Ei into Hj minus Ej into Hi into ds equal to 0, where this Ei, Hj, Ej and Hi are taken from this particular point and from this particular fields, ports. So that is equal to 0. Now this is the thing is happening for one port. Now for N port if you consider, for the N port what you have to take the sum of all the N ports. So therefore, so this equation remains same here, but only we are taking the summation from I equal to 1 to N because we are considering the N port here, but here we are considering only one port. Now next is, since Vn equal to 0 except Vi and Vj, because as a condition you have taken for Vi and Vj, that is ith port and the jth port. So this Vn equal to 0 except at this particular point. Now this equation 2 we can write it as, okay, I am repeating once again, since Vn equal to 0 for all the ports except Vi and Vj, that means except the ith port and the jth port where you are having the voltage Vi and you are having the voltage Vj, but for all other ports this voltage equal to 0. So if that is the case, then the equation 2 can be written as, okay. So this equation, so I can write it as an integral Ei into Hj into ds is equal to, because this I am taking it to the right hand side, so Ej into Hi into ds, so call it as equation number 3. Then we have one theorem, that is a Pointing Theorem. So what the Pointing Theorem I saying is that the integration from Ei into Hj into ds is equal to Pi into j. Okay. Now if this is the case, if Ei integration of Ei into Hj into ds equal to Pi into j, so then so this one and this one you can replace it by the other terms. So this one Ei into Hj, as per the Pointing Theorem, I can write it as Pij, and Ej into Hi with respect to this particular Pointing Theorem, I can write it as Pji. Okay, and then if Pij is equal to Pji, so then I can write it as Pij minus Pji equal to 0. So call it as equation number 4. Now then let us see what is this particular Pij and what is meant by this Pji. Pij is the power at reference plane I, so due to the input at plane j. That means to say that input is applied at the plane j and you are measuring the power at the plane I. Okay. Whereas Pji is you are applying the power at the plane I and measuring the power at the plane j. So that means to say that, so the first letter is indicate in which particular plane you are measuring the power, and the second character, second symbol is indicating that in which particular plane you are applying the input. That is, the first one is indicating where you are measuring the values and the second one is indicating that where you are applying the input. Now, as with respect to the equation number 4, Pi is equal to Pji. So I am writing it here, Pi is equal to Pji. Now this Pij and Pj are the powers which you are measuring with respect to whether the input is applied at the ith terminal or the j terminals. So this power I can write in terms of voltage and the currents. As you know, in electrical engineering, P is equal to V into I, power is equal to voltage into current. So, this one I am writing in terms of the voltage and the current, and this also I am writing in terms of voltage and the currents. That is Vi into Iij is equal to Vj into Iij. Then, so this one we will keep it as it is, and this particular term, so this particular term Iij I am writing in terms of the admittance. Okay? Then Yij into Vi, and here also Yji into Vj. Okay? Now, then we can write it as Yij equal to Yji. So, this Yij equal to Yj, so this I can write it as Zij equal to Zji. Hence, with these two equations, we can conclude that for a reciprocal theorem, the impedance and admittance are symmetrical in nature. So, this is what this particular whole concept is explaining. Hence, we can conclude that for a reciprocal theorem, the impedance and admittance are symmetrical in nature. Okay. So, this is all about this reciprocal network. Let's study the scattering parameters or the S parameters. Now, as you know, for high frequency networks, the Z parameters, Y parameters, H parameters and ABCD parameters are not suitable. So, in order to analyze, so these micro networks, we are using these scattering parameters or the S parameters. In a micro networks, we are considering the incident voltage and the reflected voltage, or the incident current or the reflected current, and this incident voltage and the reflected voltage are always related with each other to analyze the circuits, and these voltage and the currents are normalized in such a way that square of this particular term will give you the power in the particular device. Now, so let us consider a network where to this particular network the multiple lines are get connected, and this is the source or the input, and this is the load, and to this network, so three lines are get connected. So, this is the first line, this is the second line, and this is the third lines, and we want to analyze this particular circuit. Okay. When these three lines are get connected here, now the load ZL is connected here, and load ZL is there, and the load impedance ZL is here. Now, for this particular case, load impedance ZL is equal to the characteristic impedance, and for these two lines, the load impedance is not equal to the characteristic impedance. Now, so as I already told you that, so for the micro networks, we are considering the incident wave and the reflected waves. So, AI is the incident signals, okay. AI is the incident signals and BI is the reflected signals. Now, whenever from this particular source, the signal AI is incident on this particular junction. So, to these particular junctions, simultaneously three lines are get connected here, okay. So, here I am going to get it as A1, and to this particular line I am going to get it as A2, and to this particular line I am going to get it as A3. So, that is AI signal is passing simultaneously through the first line, second line and the third lines, and similarly reflected signals will come back from the first line and the second line and the third lines. In order to analyze this particular circuit, okay, so we are considering the different cases. Now, so let us consider case 1. We want to analyze, so this particular micro networks where the multiple loads are get connected, and you want to analyze, so this particular network using the scattering parameters. Now, let us first consider the case 1, since all the lines are terminated except the first line. So, that is all the lines are terminated to the characteristic impedance. So, except the first one, because they are not matched with the characteristic impedance, so there is a reflections. Okay. At the ith port, Bi equal to B1, that is reflection is going back to the source. Okay. So at this particular port, okay, so whatever the reflection is there, so that reflected signal is going back to source. Now in this particular case, as the load is not matching with the chaotic impedance, so due to this particular load, a signal will be reflected back toward the source. Okay. So that is Bi equal to Bi, that is if I may be 1 or I may be 2, I may be 3 or I may be 4 or anything. In this particular case, in our case is I is equal to 1, so the reflected signal is going to be B1. Now we know that the reflection coefficient is given by reflected signal divided by the incident signal. That is, reflection coefficient is the ratio of reflected signal to the incident signals. So therefore, our B1, so what you are getting, that is our B1, what you are getting it here is equal to SI1 into A1. Okay, where, so this A1 is the incident signals at the port 1 or at the line 1, and B1 is the reflected signal as you are getting, that is A1, here whatever the A1 is there, so this A1 is the signal incident to this particular line, and B1 is the signal reflected from this particular line, and SI1 is the reflection coefficient of the first line due to the source connected to the first line. That is, this SI1 is the reflection coefficient. What is reflection coefficient? Reflected signal to the incident signals. Okay. Now SI1 is the reflection coefficient of the first line due to the source connected to the first line, because now in this particular case the source is connected to the first line, because as ZL is not matched with the Z0, the a signal will be reflected back. Okay. Then so that is going to give us the reflection coefficient, that is B1 divided by A1 is going to give us the reflection coefficient. For the second case is considered when all the n-1 lines, okay, totally n number of lines are there. Now out of n lines, when all the n- lines are matched a terminated load, so the reflected signal Bi, you can write it as Si1 into A1 plus Si2 into A2 plus Si3 into A3, like this. So then I can write it as Sin into An. Since, okay, I can have any line between 1 to n. Okay. Here we are having a variable I. Since this I can have any value between 1 to n. Now the value of I can take it as 1, I can take it as 2, I can take it as 3, like this. Now considering I equal to 1 first, then go on substituting the values of I equal to 1 in this equation. Then it is S11 into A1, S12 into A2 plus S13 into A3. So like this, okay, it will continue. Then similarly, if I take I equal to 2, so then it is S21 into A1, S22 into A2 plus S23 into A3. So like this. So then I can write it as Sn1 into A1 plus Sn2 into A2 plus Sn3 into A3. So like this. Okay. So this is how. So this equation, by substituting the values of I equal to 1 to 3, you can write these values. This equation, so we'll try to represent in the matrix forms. So then, so this B1, B2, B3 will taken in this, and this S11, S12, S13, S21, S22, like this, all the values are taken here. Then A1, A2, A3 will be taken here. Now this A1, A2, A3, An, so these are your input signals, and B1, B2, B3 are your reflected signals, S11, S12, all these are your reflection coefficients. So this one B equal to, okay, in simple form, S into E, where, so this S is written, it is called as a scattering matrix, and then you have to write scattering matrix of order n by n. Once we find a relation between incident voltage and reflector voltage with the scattering matrix. Now let us consider the few things. As we know, B equal to S into A. Okay, this S is the scattering matrix which contains the coefficients. Okay, now first consider Sij. So Sij is a scattering coefficients corresponding to the input power at the ith port and the output power at the jth port. That is, Sij is indicating that you are applying the input power at the ith port and you are getting the output power at the jth port. Okay, and then Sij equal to transmission coefficients if I is not equal to J. So that means to say that from the same scattering matrix, so depending upon, so whatever the values of I is there and depending upon whatever the values of J is there, we are going to get the different coefficients. Okay, the scattering coefficients you will get when you are applying the input at ith port and getting the output at the jth port, and the transmission coefficients you are getting, okay, if the values of I and J are not same, because input port is something and the output port is something. Then one more coefficient you will get, Si is equal to reflection coefficient if I equal to J. So that is Sii and Sjj, that is your input applied is same and output taken is also same. And this Sii we are calling it as a scattering coefficients corresponding to the power applied at the ith port and the output taken at the ith port. So in this, the scattering coefficient, you are applying the input to a particular port I and you are getting the output from a particular port. So closely if you observe, so these things, you can say that we are getting the different types of the coefficients. One is the scattering coefficients, another one is the transmission coefficients, and another one is the reflection coefficient. As you already know, whenever a signal is incident to this particular network, so depending upon whether the load is matched with the characteristic impedance, so you are getting the reflected waves, where Vg is the input voltage. So now this particular input voltage is applied to this particular network, okay, where A1 is the incident signals and B1 is the reflected signals, and here A2 is the reflected signals and B2 is the incident signals. Now here we are coming across the some terms. Here Pi is written, PR is taken and PTR is taken. Pi is the incident power and PR is the reflected power, that is Pi is how much of the power is incident on this particular network. PR is how much amount the power is reflected from this particular network, and PTR is the transmitted powers, that is how much amount of the power will be transferred from input to the output. So that is the applied power in Pi minus the reflected power PR, and whereas PO is the output power what you are getting at the output. Let us consider the basic equations, that is B equal to S into A. Okay. Now this basic equation, so I am writing in this particular form, that is B1 equal to S11 into A1 plus S12 into A2, and B2 equal to S21 into A1 plus S22 into A2. Now try to simplify these particular equations, so in order to get the different parameters related with this two-port microwave device. After writing these basic equations, so try to get the different parameters, that is scattering metric parameters. Now first what you will do that, take this A2 equal to 0. Okay. When I take A2 equal to 0, now this term becomes 0 and the entire term is going to be 0. Then S1 is equal to B1 divided by A1, such that A2 is equal to. So this is called as reflection coefficient at port 1 when port 2 is matched terminated. Then make A1 equal to 0. When you make A1 equal to 0, okay, now you consider it here. When A1 equal to 0, this term is going to be 0. So then S22 equal to B2 divided by A2. Okay. So this is the reflection coefficient at port 2 when port 1 is matched terminated. Then when A2 equal to 0, so then S21 equal to, so B2 so divided by a1. Okay, when a2 equal to 0, okay, this term is going to be 0. So then s21 equal to, so b2, so divided by a1. So this is called as attenuation of the waves traveling from port 2 to the port 1. Then take a1 equal to 0. When a1 equal to 0, okay, so then, so this a1 equal to 0, then this term becomes 0. So then s12 equal to, so b1 divided by a2. So this is called as attenuation of the wave traveling from port 1 to the port 2. So that means here closely if you are observing, so this indicates your first port, okay, and this indicates even second port. So this is how, so using these equations we can calculate the scattering parameters S11, S22, S21 and S12. In the macro networks, so there are 4 types of the losses are there. Okay. Now let us consider the first loss, that is the insertion loss. So the insertion loss is always measured in dBs. So this is equal to 10 log of 10 of Pi divided by P0, where Pi is the input power and P0 is the output power. Okay. Our input power is directly proportional to A1 square divided by 2 and output power is proportional to B2 square divided by 2. Okay. Now in this equation 10 log 10 of 10, so substitute the values of Pi and substitute the values of P0. So Pi is equal to A1 square and P0 is equal, B2 is equal to P0 equal to B2 squared by 2. So then this 2 and 2 will get cancelled. We are left with A1 square divided by B2 square. Now I am dividing the numerator and the denominator by A1 square. So then in the numerator A1 square and A1 square will get cancelled. Then I am getting it as B2 divided by A1 square. Okay. Then you can write it as 10 log 10 of 1 by B2 divided by A1 squares. And we know that from the previous simplifications. So this B2 divided by B1 equal to S11. Okay, substitute B2 by A1 equal to S11. So then it becomes S11 square. Because, so this is happening because S21 is equal to S12. Therefore, insertion loss in dB equal to 20 log 10 of 1 by S12. And this is also you can write it as 20 log 10 by 1 by S21 because S21 is equal to S12. Now the transmission loss is equal to 10 log 10 of Pi minus PR divided by P0, where Pi is the input power and PR is the reflected power and P0 is the output powers. And we will try to write these powers in terms of the coefficients A1, A2, B1, B2. Then A1 square minus B1 square divided by B2 squares. Okay. So this is equal to, then what you have to do is divide both the numerator and denominator by A1 squares. So A1 square minus B1 square divided by A1 square and B2 square divided by A1 squares. So then, so this A1 and A1 will get cancelled, then you will get it as 1 minus B1 divided by A1 and B2 divided by A1. We know that B1 divided by A1 equal to S11 from the previous calculations and B2 divided by A1 is S21. Okay. Therefore, the transmission loss in dB is equal to 10 log 10 of 1 minus S11 square, so divided by S21 squares. Let us consider the third type of the loss, so that is the reflection loss. Okay. Reflection loss and it is measured in dBs is equal to 10 log 10 of Pi, so divided by Pi minus PR, where Pi is the incident power and PR is the reflected powers. Okay. So then, so this is equal to 10 log 10 of, okay, try to write this Pi and PR in terms of A1 and A2. So Pi is given by A1 square divided by A1 square and PR is given by B1 squares. Okay. Now this is equal to 10 log 10 of, so divide the equation both the numerator and denominator by A1 square. So then it is A1 square, so divided by A1 square. Okay. So divided by A1 square minus B1 square, so divided by A1 squares. Then, so this equation becomes 10 log 10 of 1 over 1 minus b1 square, so divided by a1 square. Okay. Now, this is equal to 10 log 10 of 1 over 1 minus b1 divided by a1, okay, is nothing but our S11 squares. So, therefore, you can write reflection loss in dBs is equal to 10 log 10 of 1 over 1 minus S11 whole square. Now, the fourth type of the loss is return loss. Return loss in dBs is equal to 10 log 10 of Pi divided by P0. So, this is equal to 10 log 10 of, okay, input power is A1 square and the reflected power is B1 square. Okay. Now, so this is equal to 10 log 10 of A1 square, so divided by A1 square, that is divide the numerator and denominator by A1 square. So, then so B1 square, so divided by A1 square. So, this is going to be 10 log 10 of 1 over 1 by, so B1, so divided by A1 whole square. Okay. So, this is equal to 10 log 10 of 1 by S11 square. Therefore, return loss in dB is equal to 10 log 10 of 1 by S11 square. Okay. And this is how the four types of the different losses which occurs in the micro devices you can calculate by the different equations.